Hi everyone, let's get into it. So in this video, I'm going to cover S1.4 and S1.5 from IB Chemistry. So that's just moles and the ideal gas equations. If you need help with anything else in high school chemistry, so IGCSE or IB, then feel free to send me a message on Instagram or email me. I'd love to hear from you, and I'm taking feedback on more videos that I should make like this one. Right, you can get a copy of this worksheet in the links below, so you can work alongside me filling in all the gaps. I strongly recommend that you also have access to your data booklet, because then we can look at where things are, and you're also probably going to need a calculator, so make sure you have access to your calculator. The equations for this unit are actually all found in the data booklet. So if you look in table 1, you can see the equations here. You've got the N equals M over M, N equals CV, PV equals NRT, and P1 V1 over T1 equals P2 V2 over T2. So all four of these equations that I've written in this table all exist in the data booklet. So every single one of these is in the data booklet today, which doesn't always happen. So that's nice for a change. If we have a look at these, let's just make sure we know what all of these things mean quickly. So N in all of these contexts means moles, which is measured in moles. The M stands for mass in grams. The MR is relative molecular mass. It could also be AR if you're doing it for an atom, that's fine too, and that's in grams per mole. And then you've got N, which is still moles, equals concentration, which must always be in moles per dm cubed. And then volume, which we're going to have to put into dm cubed. So something that we need to know is that cm cubed to dm cubed, which is a frequent conversion in chemistry, to get from one to the other, you need to divide by 1,000. A decimeter cubed is 1,000 times bigger than a centimeter cubed. And then obviously to get the other way, that means we're timesing by 1,000. So that's the most common interconversion that we're doing in chemistry. And then this here, you definitely need to know the units for. So P here is your pressure, and that's going to be measured in pascals. V is your volume, which in this case is going to be measured in meters cubed. Now meters cubed is another 1,000 times bigger than a decimeter cubed. So if we were continuing this conversion here, I'm going to divide this by 1,000 and times this one by 1,000. So you can see how all of these numbers kind of relate to each other. The N still stands for moles, which is nice. The R you can find in your data booklet in table 2, right here. Do not know why this is still highlighted. Let's remove that. So your gas constant is still highlighted here. So 8.31 joules per Kelvin per mole. 8.31 joules per Kelvin per mole. And that you can also find in the data booklet. So you should know that that exists in the data booklet. And then your temperature is always measured in Kelvin. So again, a conversion going between degrees C to Kelvin is that we're going to add 273 to get between the two. And then for this one, we're going to minus 273. Oh, that is not what I wrote. 273. Okay, so that's your conversions between the two. This last equation is really just a version of the ideal gas equation. So we really need to use the same units. So the pressure is still in pascals, the volume is still in meters cubed, and the temperature needs to be in Kelvin so that you can see the relationship between two gases, in this case, of the same number of moles. You've just eliminated some of the other factors of this equation. So it's just a simplified version that comes in useful sometimes. Cool, so those are the equations that we're going to use today with all of their units. So let's do some questions together. Right, let's talk about how we calculate molar mass. So you might get a question like this, which is what amount in moles is present in 2.1 grams of sodium fluoride? So the fact that you've got that it's 2.1 grams here is telling you that you're definitely using that first equation, the moles equals mass over relative formula mass. Now remember, in your multiple choice, you're actually not going to have access to the data booklet. So this equation you still need to know, and you should be fairly familiar with by now. So here the mass they've given to you is 2.1 grams. And then we can work out the formula mass just by using our periodic table and looking for what we got: sodium, which is 22.99, and fluorine, which is 19. So if we add those two together, we get 22.99 plus 19.00. Then we get 2.1 divided by 41.99, which is approximately 42. So that roughly, if we're doing this without a calculator, will give me 0.050. So if we have a look at the next question, it's saying, what is the mass in grams of 1 mole of hydrated barium sulfate given the following relative atomic mass values? So here, if they're asking for the mass of 1 mole, that's really asking for the MR, the relative molecular mass. There's nothing like more fancy. They're just asking you to add it all up. And what they're testing here is whether you know that these water of crystallization should be included in that relative molecular mass number, because they're contributing to the mass of 1 mole of that substance. So really we're going to have to do the 137 plus 35.5 times 2 plus, we've got 10 of the waters, so 16 plus 1, so 18. So overall, this is giving me 137 plus 71 plus 180. So the only number that makes sense that's big enough to fill that is this one at the bottom. Like, I don't need to fully calculate stuff to be able to work out the answer to this sometimes. You're just looking at the numbers, you're like, oh yeah, that's definitely over 300. So it must be D. We're moving on. Okay, so these questions about Avogadro's constant are sometimes really, really difficult for people to do, especially without a calculator, because the numbers are quite intimidating. So if we look at the data booklet, you can see Avogadro's number is listed here, the yellow one. So 6.02 times 10 to the 23 particles in 1 mole. So whenever you're doing a question like this, we should really kind of just write that down first. Like, if I had 1 mole of particles, that means I've got 6.02 times 10 to the 23 molecules. If I look at the options for the answers here, they all are like 2, 0.2, 0.02, etc., etc. So if I kind of transfer my stuff into the 0.2s, that makes a bit more sense overall. So if I've got 0.2 moles instead of the 1 mole, that means that I've got a fraction of this here, and it's going to relate to this number at the top. So what we're going to say is we've got 1.2 times 10, and it's going to still be to the 23 because it's just a fraction of that 6.02 at the top. This is not right, and I need to make it a full size of magnitude smaller, because I need to get to 1.2 times 10 to the 22 molecules. So if I want this to be 1.2 times 10 to the 22 molecules, then what we need to do is we need to add it another size of magnitude smaller, and so we're going to get B, the 0.02 moles. So I think with questions like this, it's really key to look at the options that are available to you. You know the answer is definitely not 2, because it's definitely not more than 6 times 10 to the 23, because you've only got 1 times 10 to the 22. So you know it's going to be smaller than 1, so you're just working out how much smaller than 1 is it. Okay, let's try another question. So this says, what is the total number of carbon atoms in 0.4 moles of octane? So what we can think about first is, if we've got 1 mole of octane, how many carbon atoms would that have in it? So you would have your 6 times 10 to the 23, roughly, 6.02 if we're being pedantic, but we don't have the data booklet, so we should be able to just approximate. And we're going to times that by 8, because in octane you've got 8 carbon atoms. So if I had 1 mole of octane, this is how many carbon atoms I would have. So in 1 mole, 6 times 8 is 48. So I'd have 48 times 10 to the 23 carbon atoms. Now that is a terrible scientific notation, so we're going to fix that. So that becomes 4.8 times 10 to the 24 carbon atoms. And that's in 1 mole. You'll notice that none of these are the right answer here so far. So what we're going to look at next is the fact that you've got 0.4 moles. I'm like, okay, cool, so I've got just less than half of this. If I look at all of these numbers here, there's really only one that makes sense, which is this one, D, at the bottom here, which is like just under half of what we started with, or 40% of it. So I'm approximating, I'm not trying to do all the math, I'm just trying to work out what I can to be able to approximate most effectively, and that is the best way to solve these questions. Okay, let's move on to empirical and molecular formulae. So empirical formula just means the simplest ratio of atoms. So what we're looking at here is we're looking at if we made all of these into empirical formula, the simplest ratio or the lowest common factor. You've got CH3 for this first one, C2H5 for B, CH2 for C, and then CH for D. So we're just looking at which ones, how they cancel down. It's asking for the empirical formula with the greatest mass. So the answer is definitely B, because that's the only one with 2 carbons in it, and that's the heaviest atom. So that's a nice quick multiple choice if you know what you're doing. Now more of a paper 2 question, so something that's going to require your calculator, or you'll be allowed to use your calculator, is a question like this where they have given you some information about a compound containing carbon, hydrogen and oxygen, and they've given me the percentage of carbon and the percentage of hydrogen and asked me to find out the empirical formula of the compound. So let's do this together. The first thing we're going to need to do is to work out the percentage of oxygen in this compound. So to do that, we're going to take our 100% and we're just going to minus the percentages of hydrogen and the percentages of carbon from this. So this overall, if we check our calculator, should give you 36.4% left over. And then what we can do is we can set up a little table so that we can compare the ratios of these. So empirical formula, we're doing the ratio of the moles. So we're comparing the moles of each of these atoms in the compound. Let's put a little line here too. And the best way to do this is to start by working out the mass or the percentage of each one of these. So oftentimes in our equation, moles equals mass over relative molecular mass, we need a mass. But here you've only been given percentages. So the reason we can use this as a mass is I'm basically saying like, meh, I'm going to assume that the compound weighs 100 grams. If the compound weighs 100 grams, then that means that 54.5 of those 100 grams are from carbon, 9.1 grams are from hydrogen, and the 36.4 grams are from oxygen. And that is all good. So you can treat the percentages as if they are masses in this case. We're then going to find the relative molecular masses. You can find these in the data booklet. I've got the periodic table. Oh, load. Periodic table here. So we've got carbon here, oxygen here, and then hydrogen up here. So we're going to take all of these bottom numbers here and put them into our table. So the carbon is 12.01, hydrogen is 1.01, and oxygen is 16.00, just straight from the data booklet. The next thing we're going to do is we're going to work out the moles of these. So the moles in this case, we're going to do moles equals mass over formula mass, just like in the data booklet. So we're going to basically divide all of these. Go back to the red. So for this one, you would get 4.54. This one's 9.01. This one's 2.275. Now it's kind of hard for me to see what the ratio of these moles are. So the easiest way to see the ratios is to divide by the smallest number. So in this case, the smallest number is oxygen. So I'm going to divide the oxygen by 2.275 and essentially like make that one 1. And then I'm going to see how the others compare by also dividing them by 2.275. Notice that I haven't really rounded my numbers too far yet because I'm not at the end of the calculation. So try to leave yourself like a good number of significant figures so that your calculations are still working out. So this one now becomes 1. I really wish I'd left myself more space here, but these things happen. This one becomes 4, and this one is 2. So that's kind of easy to see the ratio now. So the final answer, don't forget to do this, is C2H4O. The amount of times that I've seen students forget to give the actual empirical formula at the end. So this is the ratio of carbon, hydrogen, and oxygen in this compound, and that is worth 3 points overall. Okay, so you get a question like this, which is really similar to those empirical formula questions, but it's about how we calculate the number of moles of water of crystallization within a compound. So they're saying that you've got anhydrous copper chloride, and then it can hydrate, so it can get some water stuck between that ionic lattice, but we just don't know how much water. So what we can do is we can do an experiment and a calculation to work out how much water is stuck in that lattice. So they're saying a sample of the hydrated copper chloride was heated. They heat it quite strongly. So we're taking the hydrated form of this with the XH2O. We're heating it and it's becoming the anhydrous form and water. So we're basically like driving all of that water off as a gas. We don't know how much water, so that's still an X. I can't write the ratios in this equation. That's what we're going to work out using our calculation that's going to look remarkably similar to our empirical formula calculation. So what they've told you is they've told you the mass of a crucible. They've also told you initial mass of crucible and hydrated copper 2 chloride. So that will give us the mass of how much hydrated copper 2 chloride we started with. So if we do the 18.360 minus 16.221, we get 2.139 grams, which is the mass of the stuff that we started with. It then tells you what the mass was at the end. So if you again compare that 18.360 minus 17.917, that gives you the mass of the anhydrous copper chloride at the end. So this one at the end is weighing 1.696 grams. So just using conservation of mass principles, I know that if I started with this mass, I must end with this mass. So I can work out that I would have 0.443 grams of water being generated. So that's the information that they've given us in the question. Now, the reason that I say that, let me move this out of the way a little bit. The reason that I say that this is really similar to an empirical formula question is because in empirical formula, where we were comparing the ratio of like carbon to hydrogen to oxygen, what we're going to do here is we're going to compare the ratio of the ionic compound, so in this case, the CuCl2, and we're going to compare that to the water. So our table is going to look remarkably similar to how it did in the last question, but rather than it being atoms, it's compounds here. But honestly, it makes really minimal difference overall because you're just doing the ratio of moles of one to the other. I can't do anything else at this point because I don't know the X here, so I can't work out the formula mass or the moles of like this whole compound together. So all I can use is this side of the equation here. You can't do anything with that left-hand side without having that X value. So let's compare the ratio of copper chloride to water. So firstly, don't forget we do the mass. So for copper chloride, that's our 1.696 grams, and for water, 0.443 grams. So if we take the MR of both, I'm just going to write these in, but you are absolutely, so this one's your 63.55 plus 35.5 times, or 35.45 times 2, and then water comes out as 18.02. So you can work this out yourself, just check with the periodic table. I promise it's all good. And then you work out your moles just using your moles equals mass over formula mass like we did before. So we're going to do, in this case, the 1.96 divided by the formula mass of copper chloride, and then the 0.443 divided by the formula mass of water to work out the moles in each case. The moles of the copper chloride comes out as 0.0126, and this one here comes out as 0.0246. You might be able to look at this and be like, oh, I can clearly see that it's like a 1:2 ratio. That's fine. Sometimes it's really much harder to see the ratios. So just for completeness, we divide by the smallest. So we're going to divide these. Divide this one by 0.0126 and divide this one by 0.0126. And you'll see that this one comes out as 1 and this one comes out as, well, 1.95, which is basically 2. That's okay to round to 2, don't go crazy. If it's like 0.1 away, you can round it. If it's any further than that, I wouldn't recommend rounding. And so that means that x in this case equals 2. So that gives me my number of moles of water of crystallization in my copper chloride. Okay, let's move on to moles and gases. So this is a question just about Avogadro's law and gases, and often people really overcomplicate these questions. So let's try and do it in as simple of a way as possible. So it says, it gives you the equation for the combustion, complete combustion of propane. Calculate the volume of carbon dioxide and water produced and the volume of oxygen remaining when 20 dm cubed, 20.0 dm cubed of propane reacts with 120 dm cubed of oxygen. Now what they've told me in this question is it says the volume of oxygen remaining, which immediately tells me that this one is in excess. So I'm not going to count that too much. We can talk about how you would do that in R2.1 and how you would work out the limiting reagent, but they kind of told you the answer here. So if we've got 20 dm cubed of propane, what do we do with that? Now the thing about Avogadro's law and gases is that the ratio of moles is the same as the ratio of volume for gases. So what that means is that if I told you I had 1 mole of this, of the propane, then you'd be like, oh, you've got 5 moles of oxygen, or you've got 3 moles of CO2, and you've got 4 moles of H2O, and that would be probably okay. What's cool about this is that if I say I've got 5 dm cubed of propane, the ratios of the volumes work in exactly the same way because of Avogadro's law. So that means that we're just going to times this by 5 and it becomes 25 dm cubed, this would become 15 dm cubed, and this would become 20 dm cubed in this imaginary scenario. In this question, they've said, ooh, that was a big eraser. In this question, they've said that you have 20 dm cubed reacting. So I can just treat that as if it was moles. So I can do 20 times 5, so that's going to react with 100 dm cubed of oxygen, and it's going to make 60 dm cubed of CO2, and it's going to make 80 dm cubed of water. So I've already answered a bunch of these questions. Like I've already been like, oh, okay, I've calculated the volume of CO2 and water vapor. CO2 is that 60 dm cubed, and H2O is that 80 dm cubed. Now really I should have put the 0.0 on this and kept the same number of significant figures as in the question, if we're being pedantic, but you probably get the points for those either way, unless they specifically asked you. So the last part of this question says how much oxygen is remaining. So if 100 dm cubed of oxygen would react, they told me that they added 120, so the oxygen remaining is going to be 20.0 dm cubed remaining, just by doing that subtraction. So the reason this works is that like every gas under the same volume, under the same conditions occupies the same volume. So if you were to work out the number of moles, then we would be like, oh, we're going to divide by 24 dm cubed because it's at room temperature, and we're going to get the moles, and then we're going to times by 24 again to get the other gas. So if everything's a gas, you would kind of be like dividing by 24, then timesing by 24. So like, there's no point. The ratios just work as if they were moles. So we can just treat them that way, which is kind of cool. One more thing I should say about this is that these questions often come up in multiple choice because you don't really have to do much math. Like I definitely didn't use my calculator for this question. So if you see something in multiple choice like this, you can probably just use the ratios if everything's a gas. So just keep an eye out for questions like that. They are very common in paper 1. Ideal gas law. So this is the last part of this little video. So you've got PV equals nRT, which is our ideal gas law. So this question is saying what changing conditions would increase the volume of a fixed mass of gas. So if you've got a fixed mass of gas, that's basically saying that these two are fixed in space. So we're trying to work out what would increase the volume of it overall. So if we increase the pressure, the volume is going to decrease because they're on the same side of the equation. So we need to decrease the pressure to increase the volume overall. If we increase the temperature, that's going to increase the volume as well. Also, if you just think about the logic of this, that kind of makes sense. Like if you increase the pressure of something, of course the volume's going to decrease. So in this case, we want to halve the pressure and double the temperature. If you increase the temperature, it takes up more space. You also get questions like this, and it is this question is much trickier than it looks. So it's saying a gas storage tank of fixed volume contains an ideal gas at 30 degrees C, pressure of 40 kilopascals. The temperature was changed to 60. So what they're saying, and people will think, oh, I doubled the temperature. Did you? I don't think you did, because to double the temperature, we have to double it in Kelvin. We have to double it in the units in the equation, and doubling it in degrees C, not the same as doubling it in Kelvin. So for 30 degrees C, that's really 273 plus 30, which is 303 Kelvin. And for 60 degrees C, that's really 273 plus 60, which is 333 Kelvin. So we nowhere near doubled that temperature. You raised it a little bit. So if we've got our P1V1 over T1 equals P2V2 over T2, in this it's saying you've got a fixed volume, so we can eliminate that from our equation because the volume is the same on both sides. So the pressure at 30 degrees C, or 303 Kelvin on that first side, is 40 kilopascals. And then we're saying on the other side, you've got 333 Kelvin. 33, oh my goodness. 333, oh my goodness, today. Go back. 3. So on the right hand side, we've got 333 Kelvin. So what we're going to do is we're going to look at this and be like, okay, what kind of number needs to go above here to make these equal each other? So I'm like, oh, it needs to be something slightly bigger than 40, but probably not that much bigger. If we look at these options here, there's really only one that makes sense, which is this one, C, 44. So if you do the math, you can see it makes sense, but obviously you don't have your calculator in this scenario. But yeah, the answer is 44 kilopascals. They're really trying to trick you with that degrees C versus the Kelvin. Happens all the time. Okay, so let's do a calculation using the ideal gas law. So this question 11 here is actually the second half of question 6, where we worked out the empirical formula of the compound. So that's why I've written that here, because it's like part A. You work out the empirical formula, and then they give you a bunch of information to work out the relative molecular mass of the gas, which is kind of cool. So we're going to use a combination of two equations. We're going to use PV equals nRT, our ideal gas equation, and then once we've worked out the moles using the ideal gas equation, we are going to work out the MR using mass divided by moles. So we're going to use both of these equations kind of side by side. So to rearrange this formula, you get N equals PV over RT. The pressure, in this case, they have given you 102 kilopascals. So we're going to convert that into pascals, and that's going to be 102,000 pascals. We're going to times that by the volumes. They've given it to me in decimeters cubed. Remember, to get that into meters cubed, you have to divide by 1,000. So that's going to become 0.0785 times 10 to the minus 3, because we're just going to divide that by another 1,000. And we're going to divide this through by R, which is our gas constant. Remember, that exists here. We're just lifting it straight from the data booklet. So that's 8.31. And then we're going to times that by the temperature, which is here, 95. We're going to plus 273 to get that into 95 plus 273 to get that into Kelvin. So lots of unit changes here, and that's probably the point you're most likely to make a mistake. So just be really confident on those units. This comes out as 2.62, 10 to the minus 3 moles overall. So then we can use that in our subsequent equation. So the moles is 2.62 times 10 to the minus 3. And then the mass, assuming that's in the question somewhere, is 0.230 grams. And this overall gives us a relative molecular mass of 87.8 grams per mole, which is kind of cool. The next question, you can also write this as grams per mole like that. Just don't do the combination of the two, like one or the other is fine. Doesn't matter either way, the IB will accept them. The last question here is saying determine the molecular formula of A using your answers from part A and B. So the first thing that you need to do is to calculate the relative molecular mass of the empirical formula. So the empirical formula is C2H4O. If we work out the relative molecular mass of that, it comes out as 44 grams per mole, just by doing the 12 times 2 plus 1 times 4 plus 16, roughly 44 grams per mole. If we look at our relative molecular mass, we can see that this is roughly 2 times 87.8 grams per mole. We can see roughly that we're timesing that empirical formula by 2, and so that means that the molecular formula is also going to be times 2. So we're going to times it out, and the relative molecular formula of A is C4H8O2, and that is your final answer. So you're just looking at the empirical formula and seeing like how many units of that do I have, and therefore how much do I need to times the empirical formula by to get to my molecular. So it turns out there is a last little question attached to the end of this, which is suggest why some gases like water vapor deviate significantly from ideal behavior when they are cooled down. So things we should know about ideal behavior in gases is that the ideal gas law assumes that there are no intermolecular forces. So things that you might know is that water can form strong hydrogen bonds. So the chance of it having strong hydrogen bonds, whereas your argon only forms weak London dispersion forces. So what that means is that if we have water and argon, water is much more likely to stick to each other than argon are, and so that means that they're much less likely to obey the ideal gas law, particularly when they're being cooled, because when things are being cooled, that means that there's less kinetic energy for the particles, so they're moving more slowly, so that means the molecules are more likely to interact. So it makes more sense that the slower they're moving, the more likely that they are to interact. So that's all that we need to know about the ideal gas law. We're assuming that the particles have no intermolecular forces, and we're also assuming that they're super far away from each other by comparison to how big the particles are themselves. So The last little part of this is how we calculate moles for solutions that exists in this part of the syllabus. So that's using the equation that we just haven't touched so far, which is the N equals CV. So this is moles equals concentration times volume. In this question, they're asking for a volume, so we're going to rearrange that to make V equals N over C. They've given me the moles, which is 0.060 of the solute, and then we can divide that through by the concentration, 0.3 moles per dm cubed of sodium chloride. So overall, if we divide 0.06 by 3, then we get 0.2, and so B is our final answer here. You will come across a few more of these questions in our 2.1 using this equation and when we're incorporating them into titration calculations and we're trying to do ratios and limiting reagents with it. So that's it for S1.4 and 1.5. I hope that you're feeling a bit better about all this content now, but the real key to this is you have to practice more questions. So get your hand on some exam questions and do some more exam style questions on this. Let me know if there's anything else that you want me to go through, and good luck with all your chemistry.